Welcome, my online learners. Chapter 11 keeps on going on. The synapse is important. The thing about a synapse is there is a space between your presynaptic neuron and your postsynaptic neuron. The action potential will only go so far, and that space in between, instead of having this sodium electrical charges, you have chemicals that go across, and these chemicals are called neurotransmitters. So when you look at the textbook page, here is the presynaptic neuron. Pre means before. Here is the postsynaptic neuron. Now let's look at the players before I show you how it goes. You've got calcium channels, which will open. Calcium comes in. We have our synaptic vesicles containing, here's our synaptic vesicles containing our neurotransmitters. And in most situations, we're going to talk about acetylcholine, which is a capital A, capital C, small h. And acetylcholine is the most common one. Then they land on what's called a ligand gated. We talked about voltage gated in the neuron. That means it's controlled by a change in voltage. Ligand gated is controlled by a chemical. So the acetylcholine receptors will then cause the sodium to open, and if there's enough sodium gates coming open, enough sodium comes in. Okay. That was quick. I'm going to show you a video that shows it in a three-dimensional animation, and then we'll come back and summarize it again.
A chemical synapse is a special junction between two neurons that allows them to communicate without being physically connected. A synapse has several structures. The presynaptic neuron ends in a small bulb called the presynaptic terminal. The postsynaptic terminal membrane is directly adjacent, separated by a small space called the synaptic cleft. An action potential causes voltage-gated calcium channels to open in the presynaptic terminal. The influx of calcium ions prompts synaptic vesicles to release neurotransmitters via exocytosis. This neuron is releasing acetylcholine. The neurotransmitter quickly diffuses across the synaptic cleft. Two acetylcholine molecules bind with one ligand-gated sodium channel at the postsynaptic membrane. When enough sodium ion channels open, the postsynaptic cell depolarizes and the action potential continues along the neuron.
Okay, I apologize for the sound on that one, but if so it was difficult to hear. Go back, shut off the sound, and watch it with just the captions. I don't know what's going on with my sound. It started with no sound, and then suddenly the double sound appeared. I thought I controlled it. Anyway, that's why I'm putting captions on now. So if the double sound is coming through, just shut off the volume and watch the captions. Okay, quick summarization here. So you have the action potential that comes down. And remember that your action potential is due to the sodium and the sodium coming in, the gates opening and the sodium coming in. So it is the movement of ions. When it comes down, that voltage change will trigger a voltage change in the calcium, will trigger the opening of voltage-gated calcium channels. The calcium comes in. Because of the change in calcium, the synaptic vesicles move to the end, release the transmitters bind. If there's enough bound, sodium comes in again. Sodium should actually be coming in through here, but whatever. Sodium comes in again. If enough sodium comes in, it depolarizes and it continues on. Now, this synaptic cleft looks huge, but really it's microns thin, so like hundredths of a millimeter. It's very, very thin, but it's just big enough that the chemicals need to cross. Then these chemicals will keep on stimulating until the enzyme, here you can see the enzyme will break down the chemicals, the neurotransmitters, and then recycle the parts. And then it's ready to go again. Okay, and that's the synapse. Kind of confusing, but get the general idea of what's going on. Good.